Hello all. So it's 6 already, but nobody has joined the class yet. So I would like to wait for another 5 minutes to see if anyone is joining. Otherwise, I will go ahead with the class. So it's already 6 minutes past 6, and I don't see any point in waiting for any further. I think this was kind of expected because today is Independence Day. Maybe students are enjoying holiday. So I would like to carry on this class as a probably lecture class instead of a live interactive class, although I would have liked the interactive class more. Anyways, but I have a few things to mention today in class. Some of them are like the doubt which was raised in the previous class on how do we calculate the stiffness coefficients, and also I would like to discuss the week 2 and week 3 assignment problems of previous years in this class. So if in the whole meeting no participants join the meeting, I would just continue to discuss all these points and I will end the meeting at time maybe. So this time I have shifted to Microsoft Teams as the online meeting platform because Google Meet was giving some serious problems in the last two meetings. So I am using the Microsoft Teams platform now. And so let's begin the class. Happy Independence Day to all in India, and good evening. Let's start by giving a brief introduction of myself, the speaker of the class, and then we can move ahead with the agenda of today's class. So I'd quickly share my screen. Yes, my screen is visible to all. Now, first let's jump into my introduction. I am a PhD research scholar in the Department of Civil Engineering at IIT Delhi, Prime Minister's Research Fellow to be more precise, and currently I am in Toyohashi City in Aichi Prefecture in Japan to conduct research in Toyohashi University of Technology for 6 months from April to October 2023. So these are my contact details. You can contact me through the both the email IDs, the institute email ID and my personal email ID. And this is my web page from which I am showing everything. The web address can be simply seen here. Oh. Yes, so this is the web address, sites.google.com, view Sharanya Banerjee. So now let's move into my bio sketch. I am currently a student in IIT Delhi. I am doing my PhD there under the supervision of Professor Matsagar and Professor Sahu in the Department of Civil Engineering. And during my PhD, I have received an opportunity to conduct research in Toyohashi University of Technology in Japan, whereby I am conducting research under the guidance of Professor Taiki Saito and Professor Vasant Matsagar from IIT Delhi. I have received a few awards during my PhD course. Some of them are the Suzuki Foundation Fellowship, which has given me the opportunity to visit Japan and conduct research here for 6 months. Apart from that, I have the Prime Minister's Research Fellowship, which supports my PhD program in India. I have also been awarded the Professor Amya Basu Award in Civil Engineering, which is an award given by our department for excellence in our doctoral study, and a few more from past. So I have currently 3 journal publications and 3 conference publications, and I have a few lined up. So you can always check on my publications by coming into this page. My research areas are mainly structural dynamics, vibration control devices, seismic isolation devices, tune mass dampers, multi-hazard engineering including earthquake engineering and wind engineering. So my research is quite different than the topics of this class. However, the basic understanding of structural analysis and matrix methods in structural analysis is very important. So uh, so we have to learn this very nicely. So since there is no one else in this meeting right now, I would not like I couldn't get any feedback on what should I teach in today's class, what should I discuss. So I would directly move on to the lecture part of today's class. So first of all, in the previous class, towards the end, due to the shortage of time, there was a little bit of confusion on the number of members in this problem. In this problem, what are the number of members that are that are zero force members? So as we have discussed in the earlier class, whenever there are two parallel members, I hope you can see this part of the notes. Whenever there are two parallel members and there is no force in that joint, so the member which is not parallel is a zero force member. So in this case, we have 1, 2, 3, 4, 5 and 6 zero force members. Last time, due to the hurry, I actually was counting this whole member as a single member, but it is actually two members. In truss type of structures, there is no member force along the length of the member. There are only forces along the joints. So like the member force is the axial force acts along the length, but there is no transverse force on the length of the members. Only we have forces at the joints. So if there is a joint here, these are two different members. So we have 6 members, and 6 into 2, so 12 is the correct answer of the total number of zero force members. I hope there should be no confusion any further in this problem. And apart from that, I hope you all have solved the last problem which was given in the class, and you all have received the correct answer. So moving on to the class for week 3. First of all, one of the queries raised in the last class was how do we calculate okay. So okay. So I think Mr. Prabhakar has joined this meeting. So
Yeah, good evening, Banerjee. Yes.
yeah. Good evening, Mr. Prabhakar. Happy Independence Day to you. Thank you for joining in the holiday. And so first I would like to ask that do you have any specific queries for this session? Otherwise, I was going to take up your doubt from the last class itself.
No, you can go ahead, Banerjee. You can.
Okay. So please correct me if I'm wrong. Last class you were asking me that how do we get the different stiffness coefficients like 4 EI by L or 2 EI by L, those things, right?
Yes.
Yes. So today I will first explain about the derivations of all those stiffness coefficients, and not only those, like how we will find in the other cases as well. And apart from that, I will move on to the assignment problems from week 2 and from week 3. We have only solved the assignment problems from week 1 till now in the live interactive sessions. So first, let's assume that there is a beam like this. Say this is a propped cantilever beam with 2 roller supports. So now say you want to find the stiffness coefficient at for any rotation, say the rotation in this part, say the beam after the deformation becomes like this due to some loading on over the beam. So Now maybe we are interested on what is the stiffness of the beam in terms of the rotation at this point, right? So how do we calculate that? First, what we do is say this beam is named as ABC. So first what we do is we consider this beam to be a fixed beam. Okay, so after considering this, let's name this A and B. So now in this fixed beam we are assuming there are 4 degrees of freedom, one like this, one like this, one like this, one like this. So that is 2 deflection and 2 rotation at the 2 ends of the beam, A and B. So now the question is, how do you find the stiffness of the beam with respect to any one of the deflection or any one of the rotation maybe? So
it is only 2 deflections.
Yes, we are ignoring the axial deformation of the beam in this case. We are only considering the transverse deformation and the 2 rotations. If we take the axial deformations also in later classes, maybe in later weeks also, you will find out that it is similar to the truss problem and only 1 degree of freedom will be added at each end. But for the timing, let's only consider only the transverse deformation and the rotations. So for the first case, let's find the stiffness with respect to this rotation. Okay, so to find the stiffness with respect to this rotation, what we have to first do is we have to first allow this rotation. Right now, for a fixed beam, all the rotations are fixed, like all the deformations are 0, right? So we have to first allow this rotation. To allow this rotation, what we need to do is we just need to consider a roller support maybe here. Okay, a hinge support will also work similarly because we are not taking any horizontal forces. So a hinge or a roller support like this. Now what we do is we give a moment here, and this moment is called MAB. Why MAB? This is A, this is B. So this moment here, it is MAB. Now what is the deflection of the beam for this moment here? Something like this, right? The deflection and rotation at point B is 0, and we are rotating the beam for say theta A. Okay, so now for this theta A rotation, we have a MAB moment here, and for this MAB moment we also have a MBA moment reaction at the fixed end. Okay, now our aim is to find theta A, which is for this case, and subsequently theta B, and also the deflection if possible. Okay, for this kind of beam, this kind of beam. So this thing we will achieve by the stiffness method. We will first calculate what is the stiffness of the beam, and through that we can achieve what is theta A, theta B and delta. So before we start solving this problem, I would first like to know that I hope the class remembers deflection of beams, right? How do we calculate deflection of beams? Do you recall how to calculate deflection of a beam?
You're asking the method?
Yeah, different methods, and like, do you recall anything?
Easiest is moment area. So
Yeah. So first I would like to revise the deflections, because when we are trying to calculate this theta A, theta B and delta, we will use the concepts of the deflection of the beam. So I will quickly summarize that what are the different methods to find the deflection of a beam, so that when we use the method you don't feel that like we are out of place, right? So we will actually use the conjugate beam method to solve this problem. So Before getting to conjugate beam method, I will first discuss what are the different methods to find the deflection of beams. So first method is the direct integration method, the very basic method to calculate the deflection of beams. Okay. In direct integration method, do you remember like what is the formula to calculate the deflection of beam?
That's the basic m I d square y by dx. I mean ei d
Yeah.
square y by dx is equal to. I mean the confusion
M.
is
Yeah.
it is with the minus m or m it is.
Ah. Okay. Yes.
Somebody uses m, some people uses minus m. I'm not
Yes,
know
yes, yes.
what
The
is that.
notation actually varies from books to books and also like different lectures also. So, so yes, you are absolutely correct. The basic equation for the direct integration method is actually achieved from the elastic beam theory, which says sigma by y equals to m by I equals to E by R. So from this, this is the basic formula for elastic beam theory. And here, if we consider this m by ei equals to 1 by r, then we can relate this 1 by r, which is the curvature, where r is the curvature, we can relate this to the theta and y. So theta here is the rotation at any point and y is the deflection at any point. So now if we solve this, I am not going into the derivation of this, but if you solve this, you will get that d theta by dx equals to m by ei. I am using positive here, and d2y by dx2 equals to m by ei. So here positive means that the beam here, if you are assuming it to be positive, so I am taking y at the positive direction, like y in the upward direction as this as positive. So if you are taking y like this, then it is plus m by ei. If you are taking y in the negative direction, then it is minus m by ei. And here the direction of m, I think you remember, it is depending on the sagging or hogging of beam. So when the beam deflects like this, its m is positive, it is called sagging moment, so something like this. Okay. And when your beam deflects like this is actually negative, this is called hogging moment, and the moments are something like this. Okay. So just in the direct integration method, it is very simple. You just find the bending moment diagram of the beam, and from the bending moment diagram you integrate the bending moment diagram to find the deflection, to find the rotation, and to find the deflection of the beam at the various points. Okay. So any queries from the direct integration method? I hope not.
Sorry,
So
sorry,
yeah.
sorry, sorry, Mr. Manager.
Yes, yes, yes. Like, do you have any queries from the direct integration method?
No, 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 no.
No,
Only
no.
thing
Okay.
that
Yeah.
while applying some boundary condition, they take a slope as plus and minus. How to consider that plus slope and minus slope? I mean, it is with respect to clockwise rotation or anti-clockwise rotation. What we
Okay, okay, okay. So the slope is actually
because
positive.
at a point for one element it may be plus rotation, for the other element it may be minus rotation. That is the boundary conditions what we need to apply when we are. I mean, when we say boundary condition, I am talking
Yes.
the integration constant of integrations.
Yes, yes,
So
yes,
while
yes.
finding that C1, C2, somewhere we take what are the slope we calculate, we consider it as a one side plus, one side minus. So
Yes,
that
yes,
is
yes. So it actually depends on the sagging and hogging of the moment. So in this case, when we are considering this formula, d theta dx equals to m by ei and d2y dx2 equals to m by ei without the minus sign, so the slope actually goes like this. This is positive and this is positive. So anti-clockwise is positive if you are going in A, and clockwise is positive if you are going in B. So actually the curvature which you have assumed while deriving this equation is like this. So for this kind of curvature, you will get y as positive in this direction, and you will get theta as positive in these directions. Okay, so if you have a, say, beam like this, for example,
In that example, is that a theta A, theta B both are positive, or one is
yes,
positive, one is negative?
no, both are positive in this case because the curvature is like this. Okay, so I would take an example like this. Say say this is a propped cantilever beam. Here you have okay, so a prop cantilever beam with another prop at this end, say another hinge at this end, so like this. So you see, when we have derived this equation, the curvature we have assumed is like this. So in this case, here this is positive, this is positive, but in this case the curvature is getting in the opposite direction, right? So here this is negative and this is negative, like this we have to see, like what we have assumed during the derivation of the equation. Okay.
Okay.
Yeah.
Got it.
Yeah. So this was about the direct integration method. Now we'll move on to the second method, that is the moment area theorem method. Yeah. So moment area theorem again. So basically moment area can be understood from this itself. So here we have in the direct integration method, we have found that d theta by dx equals to m by ei, and d2y by dx2 equals to m by ei. So say if d theta by dx equals to m by ei, then d theta equals to m by ei into dx, and theta equals to, say, integration m by ei over dx from some 0 to L over the length of the beam. So what is this actually? This is actually the area, right? When we integrate something over the length, we get the area. So what is this area? This is the area of the m by ei graph in the beam. So very simply we can understand that, say we have a beam like this. I'm taking very simple, simply supported beam like this. We have loading like this. Any loading we can have anywhere. So what would be the deflection of the beam? The deflection of the beam would be something like this. Okay. So now with this deflection of the beam, what will be the m by ei diagram of the beam? The m by ei diagram could be something like this, anything, right? This is first, say this is the moment diagram, and if the ei of the beam is fixed, ei fixed, then we have the m by ei diagram only scaled down, nothing else. So this is the m by ei diagram of the beam, and this is a positive m by ei because it is sagging moment. Now so if we just kind of find the area between this, what do we get? What is the area of the m by ei diagram? This area is actually this part, 0 to L 0 to L integration m by ei into dx. So this area will actually give us the difference between so this is the slope of the beam at theta a, where x equals to 0, and this is the slope of the beam at theta b, where x equals to L, right? So this m by ei diagram is from, so this is the first theorem of moment area theorem. So the first theorem, what does it state? That theta b minus theta a equals to a to b So this is obviously xa to xb, say xa to xb m by ei into dx. Okay, so this is the first theorem of the moment area theorems. And what is the second theorem? So again, now if we find the
One small question here.
yes, yes, sure.
You're telling that area of that M by EI diagram.
Mm-hmm.
Area of M by EI is whether you take it slope at A or B, that area remains same, but the slope will be different, right? Both at A and B, or will it be
Yes.
same?
Okay, okay. So if you take the area, this okay, just one more. This area is always constant, right? This is what you are asking.
Yeah, yes, yes.
Yes.
But the theta A, theta B will be different depending on the loading, if I'm right.
Yes, and so this area will not give you theta a or theta b. This area will give you theta b minus theta a. Okay, you have xa to xb m by ei dx. Now this is the formula for the moment area diagram. So when you integrate from xa to xb, you will get theta b minus theta a. If you integrate from xb to xa, you will get theta a minus theta b. Okay.
Okay. That is the relative values, but how to get the absolute values, theta A and theta B?
Yeah, in order to get the absolute value, you will have to do certain tricks. You will not get the absolute value very directly. That is the reason, like if you are using moment area theorem, it is very easy for cantilever kind of beams. So if it is
Exactly.
a cantilever beam, one theta is 0, then you find the other theta as
Yes,
the
yes, yes, yes,
relative value, right? But
yes.
for simply supported beams, it is not so easy. So in simply supported beam, what you have to do is you have to find that where the theta is actually 0, maybe the midpoint if it is symmetric load, and then you calculate the half area to find the theta a, right?
Oh,
So
good info. I didn't know that. I thought if you take that complete, okay.
no, no. So if for simply supported beam, moment area theorem is a little bit
So in
complicated.
this case, you have to integrate only from L by 2 to L to get theta B or theta A, or 0 to L by 2 or L by 2 to
Yes,
L
yes,
integration.
yes.
Okay.
That should be done. Given that it is a symmetric loading,
Okay.
like the 0 theta value is at L by 2.
Then we
In
have to
that
find out
case,
the maximum moment location, and from there we have to consider it as a 0. From there we
yes,
have to integrate. Okay. Okay.
yes, 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 something like that. Okay. So this is about the first theorem, and the second theorem. What the second theorem says is, second theorem is a little bit what to say, not so simple as the first theorem, not only finding the area. So again I will draw the simply supported beam. This is the deflection of the beam, and now you have this point is, say, A, this is A, this is B, and you have one tangent drawn like this from A, one tangent drawn like this from B. Okay, this is the tangent. Then this distance, this is the point from which the tangent is drawn. So when a vertical is dropped from that point, this distance is called, say, what is it called? TBA. TBA, yes. So I would again reconfirm whether this is TBA or TAB. Yes, theorem 2. Sorry, this is actually TAB. There was a confusion. Yeah, again So this is TAB. So TAB means you have the moment diagram like this, say, of the this beam which has some loading like this, random loading. Okay, so now you have the area of whole this is the M by EI diagram. Of course, now on we'll only talk about M by EI diagrams. So you have the area of M by EI diagram. Then if you take the moment of the M by EI diagram from point A, okay, so if you take the moment from point A, that will give you the TAB. So TAB is actually moment of the area under the M by EI diagram between A and B taken from point A. Okay, so this is the second theorem of the moment area theorems. So it says that this distance TAB, this distance is actually obtained by getting the moment of the M by EI area under the M by EI diagram from the point A. So similarly, if you want to find TBA, say, so just you extend this line, this is the TBA, and in TBA you will find the moment of this M by EI diagram from point B, and in TAB you will find it from point A. So how do you calculate the moment of a diagram, moment of the area? So to find the moment of the area, you need to find what is the centroidal distance. So maybe this is the centroidal distance x bar, and so from A you will find this distance for TAB, and this distance for TBA. Okay, and actually the formula which is giving this is like we already know. Let's use this one. Okay, so we know theta b minus theta a equals to integration of m by ei dx from xa to xb. So this is the area, right? So now TBA is actually, or TAB is actually x times m by ei dx. Okay, because this is the double integration. So if it goes from xa to xb, this x will come out to be TAB equals to x bar, and this is xa to xb m by ei dx. This is nothing but the area, and this is the centroid distance of the area. So this is actually the moment of the area. Okay, so again in this case, for simply supported beam, it is not easy to directly find the deflection of the beam. For cantilever beams it is very easy. Again, you can find this TAB or TBA, anything, very easily. But for simply supported beam, you have to again calculate the tangent from this point maybe, and go and find the TBA from this point. Okay, I hope this is clear. If this is clear, then we'll move ahead with the yeah. So we'll move ahead with the last method, that is the conjugate beam method. So actually we will be using the conjugate beam method for our derivation of the stiffnesses. So before that, I wanted to just give a quick recap on the other methods as well, so that even if you want to use other methods, you can use it. Okay, so first of all, okay, so why the conjugate beam method? Like first, the double integration method was directly from the formulas, like for the elastic beam theory. Then the moment area method were to simplify the understanding of the formulas. Instead of doing every calculation each time, we can just use areas. Now in conjugate beam method, this has actually developed due to some similarities. So what is the similarities? I will write 4 equations here, and then we will find out what is the similarity. Yeah, very good. So I hope these 4 equations are quite recognizable. Like this first equation, say this is equation number 1. So this says that the first derivative of the shear force meaning V, is actually gives us the unit load on the beam. Excuse me. So I hope this expression is known to us, that the first derivative of the shear force will give us the unit load on the beam, and we also know that the first derivative of the bending moment will give us the shear force of the beam. So the second derivative of the bending moment will actually give us the unit load on the beam. So this is quite known to us. Now let's move on to the third equation. The third equation says that the theta is actually related to m by EI. Okay, this we have already seen in the direct integration method from the elastic beam theory, and again we have seen that deflection is related to m by EI through the second derivative. Okay, so what is common in this part? The common part is that dx dx, d2x d2x. So according to this formulation, say if we want to find the theta here and the y here, okay, so there could be, like, if we try to interchange these two terms, the shear force and the rotation, and the bending moment and the deflection, if we try to interchange this term, can we interchange this term? Yes, we can. Say if we say in this equation 1, in this w, in equation 1 and equation 2, if there is any w, let me write it, any w which is equal to m by EI, okay, in that case the V, the shear force, is actually equal to, what is it equal to? It is equal to theta, the rotation of that beam, of that new beam, say. So we have a real beam which has a certain loading on the beam, and we have found the shear force and bending moment of the beam. Now we are trying to find the deflection on the beam. What is the rotation of the beam? What is the deflection of the beam? So is there any beam for which the W, for which the unit load actually becomes equals to the m by EI of the real beam? So if this happens, if W becomes equal to m by EI, then we know we can calculate the shear force, which will be equal to the rotation of the beam. Similarly, if W becomes equal to m by EI, we know the bending moment is actually equal to y, the deflection of that beam. Let me erase the new beam part. Actually, this is something else. Deflection of beam. Is this part clear? If we kind of replace the W with the m by EI in the set of equations 1 and 2, then we can get the deflection and rotation by using only the shear force and bending moment of that beam. Is this part clear? Right?
Yes.
Okay. So now now let's come to the real theorem. So what does the theorem number 1 state? Theorem number 1 states that slope of the real beam is equal to the shear force of the conjugate beam. Very simple. Whatever I had explained, it is saying the same thing, but with the new term as the conjugate beam. So now we have to transform our real beam into a conjugate beam, for which we'll find the shear force and bending moments, which will give us the rotation and deflection of the real beam. Okay. So now theorem 2, very simple, same thing again. Deflection of the real beam is equal to the moment, the bending moment of the conjugate beam. Okay. So basically what it is trying to say is, we have a beam like this, we have certain loadings like this, then we have the bending moment diagram of this beam like this. Okay. Now what we do is we transform this beam to a new beam and we apply this bending moment diagram as the new W, new load for that new beam. This new beam is actually called so if this is AB, this is A dash B dash, and this new beam is called the conjugate beam. Okay. Now what it tries to say is that V at A dash equals to theta at A, V at B dash equals to theta at B, M at A dash equals to Y at A, M at B dash equals to Y at B. Okay. This is the first theorem and this is the second theorem. Okay. Very simple. But now where is the catch? The catch is, for this new conjugate beam, can we use the same support, same boundary conditions? So no, right? We cannot.
Support conditions will change.
Yeah, support conditions will change. And on what will depend the support condition?
Boundary condition.
Yeah, so the support condition, which factor will affect the support condition of the new beam? Let us all understand this fact that for this new beam, the shear force at this point will give the deflection at of the old beam. Okay. And the bending moment at this point will give the shear force at this point will give the rotation at this point, and the bending moment at A dash will give the deflection at A. Similarly, the shear force at B dash will give the rotation at B, and the bending moment at B dash will give the deflection at B. So we already know that this is a simply supported beam. A simply supported beam will have rotation in both the ends, but the deflection will be 0. Okay. Since it is simply supported in both the ends, its deflection has to be 0. So if its deflection has to be 0, say this has to be 0, then in that case, for the new conjugate beam, the moment will also have to be 0, right, at these ends. So when does a moment become 0? A moment actually becomes 0 when it is again a hinged support. So if it is a hinge, it transfers to a hinge. If it is a roller, it transfers to a roller. This will give us some shear forces, but no bending moments. So the shear force will give the rotations, but zero bending moments will give us zero deflection. So this is the way through which we actually convert the real beam to conjugate beam. Okay. So I hope this part is clear on how the support will change. So now let us discuss how the support changes. Say this is the end support. Say this is real beam, and this is conjugate beam. Okay. So for a real beam with hinge support, what will be the support condition for the conjugate beam?
Pin.
Yeah, hinged again. Okay. Why hinged again? Because for hinge support, for real beam, what we are getting the theta and y, right? We are getting theta and y. So theta, we have some value in the real beam, but y equals to 0. And in the conjugate beam, what we are asking is the shear force and bending moment. So we will have to have some shear force value, but the bending moment will have to be 0. So hinge support in the real beam will actually convert to a hinge support in the conjugate beam. This was number 1. Number 2, what will happen to a roller support, end roller support? Again, we'll see from this angle, like what will be the theta, what will be the v. So for end roller support, theta is, we have some value for theta, y is 0, right? Similarly, so for this, we'll just copy this part to this part. So m has to be 0. For shear force, will have to have some value. So end support roller, it again gets transferred into roller. Now so far so good. Let's go to hinge. Let's go to fixed support. So can you guess for a fixed support what will be theta and y?
Theta will be 0, y max.
0 and y
Theta
will be a fixed support. I'm talking about this point on the fixed support.
Y is also 0.
Y is also 0, right? So here we will have to have v0 m0. Okay. So how we will get v0 m0? Is there any support condition where we get v0 and m0, like 0 shear force and 0 bending moment? Free end. Exactly. Yeah, you are absolutely correct. So a fixed support gets transferred into a free end. Similarly, a free end will get transferred into a fixed support. Why? Because here theta also we have some value, y also we have some value. We only have we only have shear force and bending moment at a fixed support. Okay. So these were the external support conditions. For internal support conditions, let's talk about internal hinge. Okay. Internal hinge. So do we have theta here, do we have y here, and then what will become in the new beam? So in internal hinge conditions, we have y equals to 0, but theta we have a value. So this internal hinge conditions will get transferred into a internal pin where moment will be 0 and the shear force will have some value. Okay. Again, for internal roller, again we get theta, for we have some value, y we have 0 value. Again it will get transferred into an internal hinge, which will have. So here most of the times hinge and roller is interchangeable because we are only talking about the transverse reactions and the transverse forces. So if we are ignoring the horizontal components of the forces, hinge and rollers are quite interchangeable. at least till now, right? So the last one is that if we have an internal hinge, what will happen? Again, if we have an internal hinge, we actually have theta, we have a value, and then y also we have a value. So it will get transferred into a roller support. We have a value for v, and we have a value for m also in this case. Okay, so these were the different conversion of the real beam to the conjugate beam for the conjugate beam method. Okay, so basically what is the process? The process is very simple. We find the m by ei diagram. Here I have forgotten to write. We find the m by ei diagram. We apply the m by di diagram as the force to the conjugate beam. The conjugate beam supports are calculated using this concepts, and then we find the support. We find the support, shear force, and bending moments to calculate the rotation and deflection of the original beam. This is the conjugate beam method. Okay, so are there any questions till now? Yeah.
For any intermediate points, we need to take corresponding shear force and bending moment, correct? For the slope and deflections at intermediate points.
For the
Or it
slope,
is only at the ends.
yes, for the slope and deflection, we will have to take the corresponding shear force and bending moment at the intermediate point, of course. Yeah.
So this will be straightforward compared to moment area and direct integration, correct? Or
okay, yeah, this is actually straightforward, because like here we can only use the equilibrium equations to calculate the deflection and
exactly.
Deflection and rotations. We need not do any integration or anything like that. So that is why this method was also developed to like make it more straightforward, but then through a conjugate beam, like it cannot be done in the real beam itself.
Is there any case where we have to use only direct integration? Okay, direct integration also, depending on the integration limit, will get the slope and deflection at any intermediate locations.
Yes.
Yeah, but moment area is slightly confusing. So, I mean,
Yes, for moment area also you will get the similar. You can find the slope and deflection at any point, but because it is relative, so its application is actually reducing. So actually then you get like theta b minus theta a. So you have to find moment areas of 2 points maybe, and then calculate the two theta a and theta b. But it is very useful in case of cantilever kind of beams, or any, say, even after propped cantilever, so a free end at one end, so like that, anything like that. So it is actually the advantages are very case specific, but the conjugate beam method is much simpler. Like you can only use equilibrium equation to find the deflection of the beam, slopes and deflection of the beam. Yeah, and the direct integration method is also for us it is okay, because now we have
it's only academic thing we need to know that. Otherwise, it's I mean, doing that double integration, I mean, having boundary condition, finding the constant of integration. I mean, it's quite difficult. I mean, only for academic purpose we need to know that method, double integration.
Yes.
Otherwise, practical application, if you know conjugate beam, I think that should be more than enough, right?
Yeah. This is very good. However, like the direct integration, I guess will be suitable. Like if we are to calculate for big like big kind of structures, and we need to code something, we need to write some codes for the deflection. So for codifying, I think the direct integration will be much simpler. Like we can directly code. Like we have the equation for moment. We divide the equation for moment by ei, and then we integrate that within the boundary. Okay, well, that is very simple. If we just instruct the computer, it can do it for us. But for the conjugate beam, calculating, coding it will be a little bit difficult. like you have to then give a lot of parameters on how to change the boundary condition and this and that. So like the methods have their own like advantages and disadvantages, I guess. Yeah.
Okay, thanks.
Yeah. So but yes, you are correct, conjugate beam method is much simpler, and we will use the conjugate beam method to solve the problem in hand. We have this problem in hand. We are trying to find theta A in terms of MAMB, like rather we can also say we are trying to find MAMB in terms of theta A, theta B, something like that. So this problem I would again draw here. We have a roller support, we have theta A, this is A, this is B, this is MAB, this is MBA, and okay, so this is it. Any more data? Yes, we know this is L. Now we'll see a very interesting observation in this case. So can we convert this into a conjugate beam? Okay, first of all, like what is the bending moment of this beam? We have MAB at one support, MBA at the other support, and we don't have any load in between. No load in between. Okay.
Repeat trapezium. Okay.
Trapezium, yes. Okay. Yes, like your idea is correct, but here you can see this part is sagging, MAB, and this part is hogging, right? This part is sagging, the curvature is like this. This part is hogging, the curvature is like this. Let me use a different color. This part is sagging, then there is some difference at this point maybe, and this part is hogging. Okay, so one will be positive and one will be negative actually. Okay, so you are correct, it will be MAB here and MBA at the other end, but in the negative direction. So for that reason it will not be actually a trapezium. Okay, it will be something like this. Okay, so is this clear, the moment diagram? Yes. So now if we have to apply this as a load, first we have to draw the conjugate beam. So what would be the conjugate beam in this case? My straight lines are not at all straight. Okay, this is pretty straight. So in this case, a roller support will yield in a roller support as well for conjugate beam. That's fine. A free support, a fixed support, what will the fixed support be converted? Free end, yeah. So this is very, very interesting. Like this, is this a structure? This is not a structure, this is a mechanism, because it is not stable, it is unstable, right?
Yeah.
Yes. But the loading on the structure will actually keep it stable. So the loading here is MAB by EI MBA by EI. This is actually A dash B dash. Okay, this is the conjugate beam of the structure. Okay, very nice. So there is a note here, so I have written it down so that maybe if I write it down some people might read it. Is that statically determinate main beam results in statically determinate conjugate beam. Okay, let me write it down, then we can explain. Okay, so if our beam is statically determinate, it will result in statically determinate conjugate beam as well. But this beam, it is not statically determinate. This has a propped this is a propped cantilever. So the what is the degree of indeterminacy of a propped cantilever?
1.
It is 1. Yes. So now the main part. So a statically indeterminate main beam results in unstable conjugate beam. However, the M by EI loading will make it stable. So here we can see that it is one way it is above and the also below. So this kind of loading will keep it stable. Okay, this is very interesting to know. And frankly speaking, these things go away from our mind when we don't use it for a long time. But again, like when I was kind of preparing the notes on how to explain this thing, so I found this point to be very interesting, and that is why I'm writing it down so that everybody can know. So let's now let's move ahead. So now we have this beam. Okay, so again let's draw the beam. A dash, this is B. We have a loading like this, MAB by EI, loading like this, MBA by EI. We have B dash. So now what we are going to do is, let's take moment about MAB. Okay, no. So what will be the bending moment at MA dash?
It will be 0, right?
It will be 0, yes. So the bending moment at MA dash will be 0 because the deflection is 0. So now let's calculate what is the bending moment at MA dash. So if we want to calculate the bending moment from this point, we'll first find the area of this triangle into L by 3, if this is L, right? And oh, sorry,
Is L by 6.
sorry,
We need to find that distance. Then we have to take that L by 3.
Okay. Let's there is one thing which I kind of
First you need to find the bending moment of the main beam. Then we have to take that MBA type.
yeah. So we can skip that part. So I actually skipped one kind of thing. There is a way to skip that part. I'll just draw this again. So how do you calculate the bending moment of the main beam? It was MAB by EI at one point, right? And MBA by EI at the other point. Okay?
Yes.
But this is a linear kind of structure. So by principle of superposition, this will be, say, MAB by EI for one beam plus MBA by EI for the other beam, right? So actually the loading is kind of this, MAB to 0, MBA to 0. like this. Okay, so when I drawed this, I just kind of like simplified it as one single line, but if we break it down, it is a combination of two bending moments, like this and like this.
Okay.
Okay.
Yes.
Yes. Okay, so now we add this loading to the beam, just like nothing, just to make our calculation simple and not use our calculations at all. Okay, this is A dash, this is B dash, this is the conjugate beam, this is the loading. Now what is the moment at M A dash? Moment at M A dash equals to this area into L by 3 minus this area into 2L by 3, right? So half into MAB by EI into L, this is the area of the triangle, into L by 3 minus half into MBA by EI into L, area of the triangle, into 2L by 3. So this is equals to 0. Let us keep this aside. This is equation number 1. Or let us say simplify this further. So if we simplify this further, we can cut this half L square 3. So it will be simply MAB equals to 2 MBA. This is equation number 1. Fine. Now again, what would be the deflection at point B dash? It will be 0, right? So summation MB dash equals to 0. So what would be the moment from this point? Very interesting. Not like we know this, but again I will repeat. This will be area of this triangle into this distance minus area of this triangle into this distance, plus there is a V force here, shear force, right? VA dash into L. Okay, we agree?
Yep.
Yes. So half M AB by EI. So anytime, like if you feel that I am doing something wrong, which I will at some point, then you can correct me, right? Minus half MBA by EI into L, area of that, into L by 3 equals to 0. Well and good. So now the amazing part is, what is this VA dash? This VA dash is actually this theta A. Do you agree? This is the real beam, this is the conjugate beam. Shear force at the conjugate beam is the theta at the real beam. Okay, so if we simplify that, oh my god, we are already very lacking in time. Anyways, so if we simplify that, I'll just copy the answer from here. If we simplify that, what will become? 2MAB plus 6 theta A EI by L minus MBA equals to 0. If we put this one, MAB equals to 2 MBA, it will get MBA equals to 2 EI by L theta A, MAB equals to 4 EI by L theta A. Okay, so is this clear how we get this one?
Yep.
Yes. So if I'm not wrong, this was what you were asking in the last class, right?
Yes.
Okay.
Yep.
Yes, so very good. So now we have already completed what would be the relation between this theta A and MA and MB, the end moments. Now let's take on the second part. If this side is a fixed end, if this side is a roller, we have a deflection like this. This is theta B. If this is theta B, we have M, this is A, this is B. We have MBA like this, we have MAB like this. So now what is MBA and what is MAB? So yes, so I think we can directly like we need not solve it again, and we can directly write the answer. In this case it will be the same as the derivation for the last case, that is MBA will now become 4EI by L into theta B, and MAB equals to 2EI by L into theta A. So when there is theta A, the A part will have a power of like constant 4. When there is theta B, the MBA will have a constant 4. So this is the way you remember. Okay, this is clear? Yeah, very nice. So now very quickly we can also see what happens if there is a deflection. So now we need to consider that we have a deflection in the
Everything
beam.
is derived using even the slope deflection method, correct? They derived this 4A, if I'm correct.
Yes,
But anyway,
yes, exactly, you are correct. So to develop the formulation for the slope deflection method, we need to actually first find these derivations, like how the theta A and MA and MB are related, because in slope deflection we actually work with like continuous beams, right? So we consider fixed at all the ends, we find these derivations, and then we put what is MAB, MBA and these values, and also we need to find what is the equivalent load at the different ends, because here we are not considering any load in the length of the beam, we are only considering loads at the ends of the beam, right? So what is the equivalent load at the end of the beam? So I also have planned to discuss that a little bit in today's class. So like I think after my discussion in today's class, I think a lot of things will get clear on why we are taking this, and also this will help you in the further weeks of this matrix method, because this is just the basic of matrix method. If you know this stiffness, and okay, by the way, so I think we can recognize this is the stiffness, right? Moment equals to stiffness multiplied by the rotation. Okay, so now again we are trying to find the deflection. So again we would see what is the stiffness in terms of force. Here we are finding the stiffness in terms of moment and rotation. Will now find stiffness in terms of force and deflection. So say there is a support deflection like this, and this is delta. Okay, so this support has sunk by delta amount, and this is our real beam. Okay, something like this. So now what we have, because of this deflection, there will be a shear force down here, a shear force up here, and both this shear force will be equal. Okay, we have a bending moment down here, we have a bending moment up here. Okay, so now both this V and M will be equal. I think this is not a problem, because one support is sinking relative to the other, there is no other force, it is very symmetric in nature. So the shear force and bending moment at two ends will be equal. Like it is the relative displacement between the two supports. It is not like one support is sinking here and another support is kept fixed like that. Okay, so shear force and bending moments will be equal here. So now again we'll solve this using the conjugate beam method. So this is the real beam. Now we convert this into conjugate beam. So what would be the conjugate beam for this? A very indeterminate, a very unstable structure, a free end structure. Okay, very nice. So now for this free end structure, again we'll see that what is the bending moment diagram for this. This time I will not make that mistake like earlier. I will draw the bending moment diagram as the superposition of two loads. Okay, this is M by EI, this is M by EI. Again we can see this part, left part, this part is hogging, this part is sagging, so this is positive and this is negative. Okay, this is A dash, this is B dash. Conjugate beam is fine, I think. Yes. Yes. Okay, very nice. So now what would be the MB MB dash in this case? MB dash, what is the deflection of the real beam at point B?
It is delta, right?
It is delta, right? Yeah, very nice. Yeah, it is delta. Yeah, you are making the class very easy by giving the answers very quickly. Thanks for that. Yeah, so now if we calculate MB dash, how we will find the moment at these points? So again, taking the moment from B, so it will be M by EI into half M by EI into L in area into 2L by 3 minus half M by EI into L by 3. So finally you will get delta equals to ml square by 6 EI, which is equal to m equals to 6 EI by L square into delta. Very important formula, and I will just do one more step and you will find another very relevant formula for us. Now what happens if we just do where do we go? Yes, so this was in the conjugate beam. Okay, now we know M, we know the formula for M, right? So let's get back to the real beam. If we do MA equals to 0, like in real beam we can directly do the equilibrium, right? For the equilibrium condition in the real beam, say delta MA equals to 0. So what will that give us? Delta MA equals to 0. So for delta MA equals to 0, we have two anti-clockwise moments and one shear force in the clockwise direction. Okay, so it will become VL equals to 2M, and then what is V? V is actually 2 into 6 EI by L square into delta, so V equals to 12 EI by L cube. Okay, I think this is very relevant, this V equals to 12 EI by L cube. So now whenever we are developing a stiffness matrix, I think you remember the stiffness matrix, 12 EI by L cube, then minus 6 EI, not minus, plus 6 EI by L square, then minus 12 EI by L cube, plus 6 EI by L square. You remember the first line? So here it is plus and minus because the V are in the opposite direction but the M are in the same direction, so plus and plus, no plus and minus. So in the third line it will just be the opposite, minus minus plus minus. Okay, and in the second line it is actually the moment. Second line, the moment. How do you calculate the moment? This 4 and 2. Okay, so this is how you develop the stiffness matrix. I think I should not discuss any further of this because this is based on the course actually, so maybe all these things will be discussed in the different video lectures of the course. I am not sure whether it is already discussed in the fourth lecture of the course or not, fourth week lecture or not. So this is how you actually calculate the various stiffness coefficients. Okay, so is this clear now? So from whatever I have discussed today, so even if it is not a fixed beam, you need to find the say you need to find a stiffness of a beam, say a simply supported beam. You need to find a stiffness of the beam for this rotation, so you can find, right? So if it is a simply supported beam, you can directly find what is the deflection and how it is related to the different moments and forces, and then for the two end moments and forces, you can find what is the stiffness of the beam with respect to that deflection, right? So this will I think this discussion will solve like most of the problems in this case. Okay, so now next one very interesting thing which I wanted to discuss is like, here we are not considering any transverse loading on the beam, right? So every load is in terms of the end moments and end loads. So when we actually do, I don't know if you remember or not, or I think it will be taught in the subsequent lectures, like when we actually use the stiffness method or any method. So you have a like long beam with various support conditions, say dot dot dot, okay? So you just divide every beam as one element, two element, three element, dot dot dot, and then you find the forces and the forces and moments at each support, and you're trying to find the forces at moment at you're trying to find the deflection, the rotation and deflection at each support. Okay, this is what we do basically in stiffness analysis. So here we have the force vector, which is pm like this. Then we have the stiffness matrix. Then we have the displacement. So displacement will be y theta like this. Okay. So now if we don't consider any intermediate loading, then how do we calculate the equivalent loading? So what is the concept of, say, equivalent loads and moments, or these are also called the fixed end moments? Okay, why? Because we are actually means these are not absolutely equal, but we can also consider like this is related to the other. If we can calculate the fixed end moments, that is equal to the equivalent loading for a fixed condition. Okay, for a fixed condition, the fixed end moments is the equivalent loading, but for a not fixed condition, you have to see as per case. Okay, so I wanted to discuss this today. So okay, in today there is no problem with the meeting link, so from subsequent classes we will use the same meeting link, and maybe we can even go 5 minutes 10 minutes of like extend the class to complete the concepts. Last time, I am sorry, in the hurry last time I think I have confused you all a little bit. I'll just take a break from this and I'll discuss. So last class, you remember, I think we were discussing this problem number 9, and we were actually calculating what is the oh my god, we are actually calculating, what the hell. Every day I am facing new problems. So last time we were discussing this problem, and we are seeing we are seeing what is the total number of members in this case, and it is actually 12, because this member, so we can see now, I cannot point mine, this software is not working now anyways. So
Okay,
this,
can you take the right hand side? Okay, let us go one by one. Member
yes,
number 1 is 0.
yes,
That is clear.
yes,
Okay. So then what happens to member 2? Because I mean, what I got confused is we
yes.
have to indicate that member is perpendicular to those members.
uh,
Then only that member will be 0, right?
no, any, not even perpendicular. Okay, just give me 1 second. uh,
But if that member is something inclined, that component of that force will have some effect on that, right?
uh, I would just see where is my last week notes. Oh, sorry. week 2 notes. Okay, so mm, okay. I'm sorry for the software issue again. Yeah, so if there is any two parallel members, you can see this part where I am marking. If there are any two parallel members, it has not to be like parallel, perpendicular. It can be in any direction, but it will be 0. Why? Because if say there is a parallel member like this, and there is like this, and there is no external force here at this point, so by no way this parallel member will actually cancel out the other one. There is no component of force to give for this member.
Now, how do we apply that to sigma v and sigma h is equal to 0 at that point? So if I got an inclined member, that definitely that will have a component there.
In the horizontal direction, right?
Yeah, definitely, yes.
Yes. So it will also have a component in the vertical direction also.
Yes.
Yes.
Horizontal direction.
Yes, we have a
So
component.
that will become a 0 only if it is perpendicular. Then what happens? That sigma h component becomes 0. Definitely that force will be 0 in that.
No. Let me explain. Like we are talking about a member like this. Okay. So for the inclined member, there is a horizontal component,
Like
and there is
theta,
a
at some theta angle.
yeah.
Not
There is
equal to 90.
yeah. So you're talking about there is this horizontal component and this vertical component. Okay.
Yes.
So you are talking about like this horizontal component will also add to the scenario.
Yes.
But this vertical component, this has to be 0, right?
Why? That is what I'm telling.
Yeah, because there is no other force at this point. So what will this vertical component be balanced with?
That will become balanced with that other wherever it is connecting from that end, it will have vertical component.
No. Say we have.
Well, I'm getting confused.
No problem.
What is that theorem? I mean, if I understand correctly, even the third member is perpendicular to that member, then only that member will be 0.
Say you have a 3 members like this.
Yes.
1, 2, 3. Okay.
Yes.
So these 1 and 2, these are parallel to each other. Okay. And 3 is not parallel to any of them. So 3 will have a say horizontal component and a vertical component.
Correct.
Yeah. So
Yes.
say this is 3v, this is 3v, and this is 3h. Okay. So now if you do sigma fx equals to 0, you will get
3h plus 2 is equal to 1. It is.
Yes, 3h plus 2 equals to 1. So if you do sigma fy equals to 0, what will be the answer?
Okay.
Sigma fy equals to 0, 3v equals to 0, right? So if you do sigma y equals to 0, 3v equals to 0, because 3v doesn't have any force to balance it out. So if 3v equals to 0, there couldn't be any theta greater than 0 which will have some force here. So this 3 will have to be 0.
Okay. Then how do we apply that logic for that member 2?
Yeah, so now let's get to the member 2. So here
member 1 it is clear, it is 0.
Member 1 it is clear, perfect. In member 2 we have now 3 members left, like this. Okay, is it visible? 3 members like this.
Yes,
member
yes.
So now member 2 is also 0. Is it clear?
Because we are considering that member 1 is 0, then of course.
Yes. Member 1 is 0, now member 2 is also 0. Okay.
Okay, clear.
Okay. Now member 4 and member 6, 5, 6. Member 4 and member 5, 6. Member 4 is 0.
Okay.
Okay. So
then for member 3 will be 0.
Member 3 will be 0. Okay. And now if member 3 is 0, yeah. So now member 5. Member 5 and there is no other thing. Member 5 and these two members. So member 5 will be 0. Here 1, 2, 3, 4 are 0. Member 5 comes and joins these two parallel members, which has no joint force here. So member 5 has to be 0.
Got it, clear.
Yeah, okay. So we have 6 members here, and 6 into 2, 12. That is the correct answer. Yeah?
Agreed.
Okay. I thought that there was a little bit confusion because of the hurry last time, so I just explained it one more time. Anyways, so now I don't know whether, I think this will not work today. This is only read-only mode now. Okay, I will upload till this part, and now let us discuss the other part. Some blank pages maybe. Do I have any blank page? Oh.
If possible, next week can we discuss on that week 2 assignment? Anyway, it is grading is over now for that.
Week 2 assignment for this year?
Yes.
Okay, yes, no problem. We can discuss like
Grading is done. Grading is done already in that one.
Okay. I'll check that and I will do. I will. Okay. So let's only. Okay. I don't know how to use. Every week, like there are some technical problems from my end. I'm very sorry for that.
What happened now?
That notes software is not working. It's saying that I need to take subscription. Anyways, so yeah. So we were talking about the fixed end moments. Okay. So I am discussing it here, and then I will upload this file also, so you can find it here. So again, we have a fixed beam like this. We have, say, a load P like this. We have moment, shear force and bending moment like this for this load. Okay. And this is L by 2. Okay. So now we want to convert this load P into the end forces and moments instead of using it as a member force or moment. Okay. So the objective here is clear, right? So what would be the equivalent moment at the ends and equivalent forces at the ends to calculate this, to find the effect of this load P. So for this, again, we take the help of a conjugate beam. So again, fixed, a conjugate beam would be free. In that case, we have a moment M here, a moment M here, moment M in the left side, it is sagging or hogging. Both are hogging. Okay. So like this. Okay. So M by EI. In this direction, This is fine for the two moments. And then we also have a load P in the middle of the beam. So that load P, how will it cause the bending moment? It is a sagging moment. And what is the maximum bending moment for a load P at the midspan?
PL by A.
PL by 4 EI. Yeah. So this is a concentrated load, so by 4. So if it is like uniformly distributed load, then it is WL square by 8. So WL is the load and into L by 8. So PL by 4 and divided by EI for the conjugate beam. Okay. So now very simply we want to find what is the equivalent moment here. So we do sigma. Now we do V A dash. This is A dash, this is B dash. So what is V A dash? V A dash is the rotation at a point A in the main beam. So rotation at point A equals to 0. So V A dash equals to 0. What is V A dash? If we solve, V A dash would be half into PL by 4 EI into L. Okay, this is the area, minus 2 into half into M by EI into L, okay, equals to 0. If you calculate that, M equals to PL by 8. Okay, this is the fixed end moment due to a concentrated load P at the midspan. Okay, I think this also you might recall, you have used this in the slope deflection method also, and you will also use it in week 2 assignment problem, I guess. So this was for the concentrated load. Then let's move on to the UDL. So if there is a UDL, say like this, W, this is A, this is B, this is V, this is M, this is V, this is M. So what would be the fixed end moment for a UDL load? So for UDL load, what will change will be this PL by 4 EI will be WL square by 8 EI, and the area of a parabola, this will become a parabola. The area of the parabola will become 2 by 3. Okay, so 2 by 3 W. I am skipping some steps here.
Okay.
Please, yeah, I hope that is okay. So minus 2 into half M by EI into L equals to 0. So the answer finally which we will get will be
12.
Yeah, M equals to WL square by 12. Okay, so this is how you calculate the fixed end moments. Now you can calculate for a triangular load, for a trapezoidal load. There are many options, and all these answers I have already attached this in this PDF. So I will upload this PDF and you can find the answers for all the fixed end moments. Okay, I hope this will be useful to you. Although mostly we will only use the concentrated load and the uniformly distributed load, which I have already derived here. Okay, so I guess this is fine, the explanation till now. Okay, so that was all which I needed to explain in this class. Now let's move on to the week 2 problem solving. Okay, previous year's problem. So last time I was taking up a lot of time in drawing all the problems. This time I have made a PDF document which I'll just read the problems and we'll solve it together in this sheet. I'll upload this sheet as the problem sheet. Okay,
you just zoom that. I can't read that.
Okay, is this visible now?
Better. Yeah.
Okay, so this is the maximum zoom which is possible, I think, if it needs to be in one window.
That's fine. That is fine.
Yeah. So now first question was, what is the primary unknown in the analysis of structure by displacement method? So I don't think it needs a little bit of time also. Yeah, displacement, right? Very simple. Then second question is, how are the additional equations obtained to solve a problem by force method along with the equations of equilibrium? So yeah, what are the additional equations that are required for
compatibility, displacement
compatibility? Very good. So how many numbers of redundant forces to be considered and removed for making a structure statically determinate?
As many numbers.
Yeah,
correct.
Very yeah. As many number of static indeterminacy. Yeah. So then, what can it be said? When can it be said that a structure is stable? We have 4 options here.
I think it is D.
uh, obviously, yes. After visual inspection, along with, like, if we know that the unknowns are greater than or equal to the available equation. Okay. So which figure shall we use to determine the elements of the second column, which corresponds to the degree of freedom number 2 as shown in the structure of the flexibility matrix? Okay. So we want to determine flexibility matrix for column 2. You are saying option D or B? B, yeah, absolutely correct. B. So if we want to determine the flexibility matrix, then we have to kind of okay, I'll draw this beam here. I'm just explaining if somebody joins online, means sees this YouTube video online. So if we want to derive the flexibility matrix around with 2, we have to release this displacement and we have to rotate it like this. Okay. So this is done. Now which redundant reactions or forces should not be removed to make the structure statically determinate so that the structure does not become unstable? So which should not be removed in this case?
1 and 5.
1 and 5, yeah. Very, very simple questions. 1 and 5. So if you remove 1 and 5, what will happen is, yeah, you will have a roller, then the structure will become unstable. So we do not want this. So stiffness matrices before imposing boundary conditions are?
Is symmetric and singular.
Exactly, yes. So when we have a stiffness matrix before we have the boundary conditions applied to that, so we have say if we have 4 degrees of freedom, 2 here, 2 here, so it will be a 4 cross 4 matrix, and this will be singular. Why it will be singular? There is no solution possible for this condition because there is no boundary condition. This will have rigid body motion. So therefore this stiffness matrix will be obviously symmetric. Why symmetric? Symmetric because of the Maxwell's reciprocal theorem, and singular because solution is not possible from this scenario. If it is singular, you cannot take the inverse of the matrix and hence you cannot solve the matrix. Okay. Now how many degrees of freedom are there neglecting the axial deformation of the beam? This is a beam. How many degrees of freedom are there?
Neglecting the axial deformation.
Yes.
It will be 6.
No, actually
4. No, 4 is not there.
Yes, so actually the degrees of freedom will be 0. This is, now we are not solving it for stiffness coefficient or anything. We are just finding out what is the kinematic degrees of freedom. So the kinematic indeterminacy of the structure is 0,
okay,
right?
They're calling, okay, degrees of freedom. Okay.
Yeah. How many degrees of freedom are there?
So it is a 0. It is
0. Yes. Okay. So this question, I have left a lot of space in this question because I wanted to solve it, but now I have already explained you how to find the different equivalent loads and moments at the supports. So for this problem, what is the equivalent joint load at joint A of the structure? What is the equivalent load here? Okay. So how do we find the equivalent load here? The equivalent load, say VA equals to, it is a UDL, so it will be WL by 2. So what is WL by 2?
It's 24.
Yeah, it's 24 kilonewton, and it will be upward or downward? It will be downward. So we are left with option A and option C. Okay. So it will be downward because the UDL is downward. So this equivalent end load will be VA equals to WL by 2 downward. And what will be the equivalent end moment? we have just derived a little bit earlier. It will be
square by 12. The option is
WL
A,
square by 12.
24.
Yes, 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 you are absolutely correct. Option is A, WL square by 8. So it will be coming to 96 kilonewton meter, and it is
The
actually,
confusion is reaction will be anti-clockwise and applied load will be clockwise.
yes, 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 you are absolutely correct. Yeah. So if it is a equivalent load, it will be clockwise in the same direction as the load on the structure, but the reaction would be anti-clockwise. Yes. So this is the correct answer. Very good. Now, next problem. Suppose a structure has static indeterminacy of 3 and kinematic indeterminacy of 2. How many redundant should be considered to solve it using displacement method of structural analysis?
This 2 or 1, because displacement we need to release that to 2, right?
If we want to find in the displacement method,
Kinetic indeterminacy is 2, that we have to allow that. Then only we can.
yes, 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 yes.
That was the confusion probably in the last current week 2 thing.
Okay. So yeah, last week what was the confusion? Can you
I
say?
don't know. I forgot that. Probably next week, if you find some time, 5 minutes, we can run through that in the next class.
Okay, sure. So yeah, so in the displacement method of structure analysis, what is the unknown here?
It's kinematic indeterminacy, right?
Kinematic indeterminacy, yeah. So the like how many redundant should be considered, that is the kinematic indeterminacy. Okay, so only like we'll correspond to the unknown and find which indeterminacy we should consider. Okay, so now, is this truss stable? If not, which additional redundancy can make it stable?
That both are pin support.
Yes, both
C
are
or
pin
B?
support. Yeah.
Then it is a stable, correct?
Yeah, it is stable. Yeah, only this was given to confuse, I think. It is stable because it is a pin support. So even if there is some,
Even if it is one roller, is also it is a stable.
yes. So it is no. Even if it is one roller, it is stable. No, I think if it is there is one roller, this will just slide below. Okay.
No, it will not.
Because of the forces here.
Okay, got it. Because you are not connecting these two members.
Yes,
you connect
yes.
that, then okay,
Yes,
got it.
yes.
Yeah.
So this structure is stable. So this is a truss kind of structure. That is the reason. Yeah. So how many numbers of degrees of freedom to be removed to make a structure statistically determinate? We already, I think, went through this question. Yeah, I think this question is repeated. So it is as many numbers of static indeterminacy. Then what will be the kinematic indeterminacy? Ignore axial deformation. Again, I think, okay, no, this is not repeated. Yeah.
It is 1.
Yeah, it is 1. Last time there was a fixed support here, this time there is a roller support here. So the kinematic indeterminacy for this kind of structure, we only have one rotation possible here. So this is the kinematic indeterminacy, and the answer is 1. So this is what we have solved for the fixed end moment. This will be present in the week 2 problem sheet. Okay, so if you need to refer to the notes, you can use this. So this is all from week 2. I also have the week 3 problem sheet. So should I discuss that today or maybe in the next class, whatever you would like?
I think we can discuss next week.
Next week. Okay, no problem. And I would like to thank you very much for joining even on a holiday.
No, that
yeah. So for me, I guess it's not a holiday, but in India, it is a holiday. So thank you very much for joining. I would now stop the meeting here. If you don't have any further questions, Do you have any further questions?
No, 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 no.
Okay.
Thanks, sir.
And
Such a period of time. Thanks.
yeah, and do you have any suggestions for next week? Any discussions you want in the next week? Because today I prepared something which I could explain, relating to the old topics and summarizing everything. So maybe if you want some other topics to be discussed, I can do that in the next class also.
Let me think over it. I'll come back next week if I need some basics or
Okay,
anything.
okay, sure,
Okay.
sure, sure. And
And
anytime you can also send me one email. I guess you have my email ID. So if you have any problem, you can send me the email. I will discuss that in the next class. If you don't have the email ID, I can just write it
what
down
is
here.
the recent reference textbooks for all these basics, conjugate, or still we are going with the Wang old?
Uh,
Or is there any new textbook or new reference which is easy to?
no, I was actually looking into the book by Hibbeler, Structure Analysis book by Hibbeler, which is
Okay.
currently in its ninth edition, I think,
Okay.
2015. So
Okay.
you may have a look at that. That is not quite difficult. And apart from that, I think that is simple enough. Whatever I discussed in class were mostly like summarized in terms of those. I have changed my notations a little bit, but the concepts were
That's okay.
similar. Yeah,
That's okay. That's fine.
yeah,
Thanks.
okay.
Thanks, Mr. Manoj. Okay.
Yeah, yeah. I have given the email ID in the chat box, so you can email me in case you need any
Sure. Sure.
specific discussion. Okay.
Sure. Sure,
Yeah.
sir. Okay.
So I'll
Thanks.
I'll
Thanks.
end the meeting. Okay. Yeah.
Thanks.
Thank
Thanks.
you very much for
Good night.
joining.
Good night. Good night.
Yeah.
Bye bye.
Good night.